We will do AI research step by step in this video on the next big thing in AI. Elon Musk just said that they are gonna be replacing tokenizer and tokens in LLMs with direct byte inputs. So it makes sense because digital world is made of bytes. But I want open source to lead in science, and I want also latest science to be open source. So we will try to figure this out before then. And that's good for everybody because these companies like OpenAI and xAI will get free research and they can invest money into products and they can build better products and make a lot of money. And everybody has access to the latest, greatest open science. So in this video, publish your first LLM. I have my LLM that I coded. I showed you how you can train it, how you can publish it. So right now we will try to replace tokenizer in that LLM with direct input bytes. So just inputting bytes instead of tokenizer directly. Tokenizer is creating a lot of problems for everybody. So people already want to replace tokenizer. It just works best right now, so it's not replaceable right now. This is the GitHub repository. I will leave it below of this research. So I'll just try to do my best here. This is gonna take months and more people, maybe PhD students, to figure out. So you can fork the repository. I'm gonna try to explain how I do all of this. And you will learn so much about LLMs and neural networks and AI research and everything, not just about tokenizer and bytes. So first, I want to plan our research. So I have this prompt. I had some mentorship before on AI research, so I'll try to structure. I'm going to try to replace my mentor with ChatGPT. It sounds a bit funny, but so when you're doing research, you need to plan the research. So I have this prompt that will help me plan my research and think about it. Because main advantage of humans over AI is we have this deep intuition, thinking, we have so much more context, but we can use AI for these specific tasks. I explained that I want to feed bytes directly into LLM without tokenizer, and I want it to give me some templates, some questions to think about. So I first want to think about and understand research questions. So we don't want to just try coding something. We need to first think and understand what the problem is. We will spend a lot of time understanding the problem and what we're even trying to solve. One of my ideas for solving this is by Meta, Byte-Latent transformer, where I would do something similar. Maybe train some small neural network to predict the next byte. And it's doing the same thing as the big large language model, but this small network, when it gets confused, so when it becomes difficult to predict the next byte or perplexed, then we will take those group of patch of bytes before it got confused, encode them into latent vector as if this patch was a token. So then if there is a bunch of bytes that are easy to predict, it all goes into single vector. But if there are some difficult bytes, then only those bytes go into single vector. So we can use less compute per byte for easy bytes and more compute per byte for difficult bytes. So that small neural network will encode this. And then we have these vectors, we process them as if they were tokens. So if this is a bit confusing, don't worry. We are trying to understand this, and this is taken from Meta's paper, as I mentioned. I will use ChatGPT 4o on LM Arena. I like 4o a lot. It's writing it in very simple and organized way. That's why I like it. I'll also use GPT-5 High. I think 4o will be better, and I'm gonna use Grok 4. I could use other ones, but I'll try to compare these three, but I'm gonna start with 4o. But it doesn't matter which one we use because this is just inspiration and we are gonna be thinking about the problem. I'm not even gonna try too hard to replicate Meta's approach. I'm gonna try to follow my curiosity. I think that's a more motivating and more sustainable way to do research. So I can read Meta's approach, but if I don't believe it, I will not 100% do the same. I will do what I believe in. I made the Notion page, so here I will structure my research, replacing tokens with bytes, LLMs, VLMs, other foundation models, everything. Honestly, I've been trying to use AI, or either I cannot prompt it well, but I don't think it's too helpful for me, but maybe I'm just not prompting it well. I got a different idea. So in my last video, I coded this Byte-Latent transformer. So it's gonna be this video, and I'm just gonna first try to understand, because Claude coded it. I told it what to do, but I didn't understand 100% what it did. So I started with my own LLM and gave it a research paper by Meta and told it to code this byte latent things with bytes. I'm gonna use Opus 4.1 here. I think I like it for coding, and for writing it's really good as well. Let's understand how it works so we can change it and create experiments with it. So we have text hello, and then convert to byte sequence by using this list, encode in UTF-8. We do have it right here. So this will give us result list of bytes, 70, 201, 108. So these are all of the ASCII values for these letters. There is 256 in total. Because there are in one byte 8 bits, you can have 256 different numbers. So the way we will deal with those 2 byte or 4 byte letters and characters, we will just pass in bytes into transformers. So we don't care, like, if there is one character made of 2 or 4 bytes, then transformer will learn to do it, to like recognize it by itself. You see here with 1 byte we have this ASCII range, 2 bytes we have different letters, 3, 4 different symbols, characters. So we will just use this 1 byte range for now. But I feel like if the text has these 4 bytes, it will just get encoded as these 1 bytes. I think so we can process any type of information. You see how Opus 4.1 explains it nicely step by step. But GPT-5 High, it's more confusing. It doesn't even know what I asked it. And Grok 4, there is too much text. It's not so nicely structured. So I need to read a bunch of text that's not so useful to me, I feel like. When I read Opus 4.1, everything is so useful and concise. So then we will group bytes into patches, like groups. For example, we can use a group of 8 bytes per patch. I don't want to have fixed size, because I want transformer to allocate compute depending on complexity of the bytes. So if it's too complex, then it's gonna group fewer bytes and process fewer bytes together. But if it's easy to predict bytes, then we can put more bytes. If it's like some easy sentence, we don't need so much compute. So we can put more bytes into the vector embedding to be processed, to be generated, to be predicted, to be processed. Okay, but this is example. Patch size 8, we have 5 bytes. And we have this pad token it's just a token to pad them to 8. And my research idea is, should we replace end of sequence with pad token? So we have 2 extra tokens. We have end of sequence token that just eliminates end of sequence, which I don't see here for some reason though. We'll see about that, but I remember in my code there was 2 of these. So maybe we can just use one. Quen is using just one for both of them. Or we have this other patching method, which I like more. We could use this, or we could use even better one if we invent even better. So we have these patches, and then based on perplexity or difficulty of predicting, for example, this batch, if it's too difficult, then we would group these 2. And then if this one is difficult and these 2 are easy after that, then we group these 2 together. So the beginning byte will be difficult to predict, so we start group patch from there, and then as long as it's easy after that, we group that together. So if all of these are difficult, we would separate them into different patches, then we would process each one individually. But if a bunch of them is easy, we process all them together into a single vector embedding. These are all ideas in byte latent transformer by Meta. Then we have this small encoder that's gonna convert patch of bytes into embedding to be processed by the transformer. It's the same type of embedding as in token embedding. So if we have a patch of bytes, then that's gonna go through the NN embedding layer from PyTorch. Vocab size is 58 because we have 256 bytes and 2 extra end of sequence and pad tokens. And then dimension of this encoder 192. This is how it works right now, although this is to be experimented with. So each of the bytes gets its own embedding. So this is like we have tokens, and each token is connected to its own vector embedding. And these are learned as the model trains. So I'm thinking here, I need your ideas. So one byte is a lot less clear and can represent so many more things, can build so many more things than one subword token or a word token. So maybe byte embedding should be larger, I'm not sure. But maybe it could be smaller for some other reason, I'm not sure about this. Then when we replace each byte with its vector embedding in the sequence, then we pass that through local transformer small. So this is I'm pretty sure this is separate. This is separate transformer that's just encoding patches. So it's a small transformer, 2 layers, and each byte attends to other bytes in the patch. So this is like self-attention. So I'm already thinking maybe this can be done in even a different way. But I guess we still want to just try to predict the next patch, or next byte, I should say. But wait, how do we determine this patch? We should have like the patch size. So this is converting a patch of tokens into the embedding, but before that we needed to like determine the patches, which we skipped in this explanation. Anyways, let's say we already have a patch. We'll deal about this patching later. So mean pooling, average all byte embeddings, single 192 dimension vector per patch. Just averaging all of the embeddings. Is there a better way to do this? Well, we don't want to use neural networks if we don't need to. It's more computationally complex. But averaging is like the way to do it. I'm not sure. But also like there is significance to the position of bytes. So by averaging, we lose the information about position. So averaging, not sure if this is the best way. So there is a bunch of proposed solutions to both of those problems, but we will not deal with that right now. I think just by putting it even this way and trying to understand this method and maybe one more method will teach us more than trying to understand 1,000 different methods. And we'll be able to come up with a good solution. We need to understand how like all of this works as opposed to trying 1,000 different methods. And then after the average is found, then we project 192 dimension average to 384 dimension of the main model. To me, this is just one projection layer, I guess. So the problem I see here is it feels like we have 2 parts that are glued together with this layer, as opposed to one unified thing. Maybe, but maybe not. Maybe this is like a small part, so maybe it is unified. Maybe it's small enough, I'm not sure. We did get a pretty good understanding of this. So each byte has a corresponding vector embedding. We look at the sequence of bytes and replace each byte with its vector embedding, average all into a single vector embedding, and then project from that byte vector embedding to the model internal embedding. So this internal embedding is the transformer, the big language model transformer internal embedding. It seems very simple. It's good. We want to have like as few neural networks and learning as possible. So this averaging has that benefit, but maybe it doesn't preserve information about the sequence of bytes, but also this is maybe just supposed to replace a token. So maybe this average, we don't need so granular information about bytes. Maybe this would just like keep the small piece of information that's necessary. And then we get this patch embedding 1, patch embedding 2, or patch 3 embedding, etc. Goes through our large language model. We have the classic causal attention, and then the classic, we predict the next patch. And then we take this predicted patch, we map it, project it back to the patch in decoder dimension. Then we have autoregressive byte generation from that single patch. So we have a patch embedding, we want to predict sequence of bytes. During the training, we will show it the real bytes. So this decoder will learn to predict those bytes from this patch embedding. So that's what teacher forcing means. It means giving model the correct answers during training, the target bytes. Let's say we are decoding a patch that should output high. So it's 72 and 105 ASCII numbers for age and eye. So position 1 generate age from scratch, position 0, and position 1 you generated age to generate eye. So when generating I, it gets both the patch embedding and the previous bytes, which is age. Problem, if we generate X instead of age, the error compounds now to the rest of the bytes. And teacher forcing means even if we predict X, we will, for the next byte in training, we will replace it with the correct byte age. So we will use the correct bytes during training as input, not the previous predictions. For my research, I'll use Novita AI GPUs. They do have cheapest GPUs. I'll use this template and I'm gonna select spot 50% off. And then I'm gonna choose this one. It's only 18 cents. This is the cheapest on the market. And next, and deploy. If you use my affiliate link, they'll give me 10%. It's their money, not yours. You can support me, do more research this way. But even if you don't use my affiliate, I think this service is best because it's cheapest. I'm gonna click here, connect. You need to set up your SSH here, ask ChatGPT if you don't know how to do it. But now that I have it, I'll just copy this and put it into terminal. Then I told Claude Opus, I want to do research on this. For now, I want to just try to change different hyperparameters, different settings, and I want it to be minimal. Give me a list of things to try and explain it with Markdown. Don't just write code, because Claude Opus can sometimes just write code. First, he's suggesting me to try different thresholds for the entropy-based selection of the patch sizes. We did not explain how this works though, so let's explain that. So entropy measures uncertainty or unpredictability of the system. Low entropy, next byte is predictable. Keep adding to current patch because it's easy to predict. High entropy, next byte is hard to predict. We want to start a new patch because this is like a separate concept. Maybe we're talking about different thing now that's not so related, or some difficult thing that needs more compute, so we want to separate this difficult thing. If we have a sentence, in the morning sun will, it's very predictable word rise there, so that's predictable, that's easy. So that would be example of something easy to predict. But there are some other examples where it's difficult to predict, so we want to separate it. So when you are reading and you see a surprising word, unexpected word, you also need to think a bit more about this. So if we have beginning of the word hello, so hell, then O is easy to predict, low entropy, and then the next byte, many possible options, high entropy. So O would get low entropy like 0.5, and this after the would get high entropy around 3. So this is what it would look like. Let's say we have hello world, and then this is what entropy would look like. Predicting age from nothing, high entropy. There are many possible options from nothing. Then E, it's a bit lower entropy because we have age now, options are limited. And then L, lower entropy, L another, so this is low entropy. Okay, now after hello, maybe there is a bit more entropy here. Maybe there could be like comma here or something. And then after hello W, this is very uncertain. So then entropy, but then hello world, O after W, that's very famous. So that's low entropy. And Claude Opus 4.1 is the only LLM that can explain this well. I can't believe it's so good. We can have threshold 2, so we split whenever entropy is more than 2. So we split age, and then LO, and then world. This is because age is difficult to predict, so we can use a lot of compute just for this age. but then this is a bit easier to predict, so we're gonna use less compute for this part. I mean, same compute as age. You can pause to check this, but I'll just go on. For example, repetitive bytes would have low entropy, and then random bytes will have very high entropy. This is just an example. But maybe model would learn. Maybe it will figure out, okay, I'm just writing random bytes. So now it's not gonna be so high, it's gonna be low entropy again, because it can easily keep predicting random bytes. Now explain my code in my code for calculating this entropy. So guys, even though we are just trying to understand this single method of solving this problem, we are actually understanding the whole problem right now, just by understanding one method. So don't think, oh, there is 1,000 methods, I don't know which one to learn. Actually, any method is good to learn because you are understanding the problem now. So in order to calculate entropy, we will use Byte-LM small byte level language model for entropy calculation. It's different, so this is the small. So this is very small and it needs to be very small. It just needs to be good enough to calculate entropy and predictability and perplexity, not to actually learn how to generate language. So we're gonna use the big one for that. In my code, we just train it we first convert my data into bytes and train it for 2000 steps, which is a bit low on one GPU, but it's good enough. And then we save that model. Then I have this calculate entropy function. It just calculates entropy. So the way it works is it first converts these raw logits into probability distribution. So they all add up to 1. Then it takes log of probabilities. It's more numerically stable. So it goes like this. And then the entropy formula, it's gonna give you big number if these probabilities are similar to each other. And it's gonna give you a low number, a low entropy, if there is like one probability that's very high. So model is certain which byte is next. But if model is uncertain, all probabilities are kind of the same, then high entropy. So then we calculate entropies when we are splitting into patches. And there is this splitting logic. So if entropy of the current byte is higher than the threshold, then we will split right here, append to the list of patches and start a new patch. And we also have so if it's not too high, then we just add this byte to the current patch. And we have this hard limit of 16 bytes per patch maximum. My code automatically picks the best threshold, so we have patches around size 6 bytes. But maybe this is one area we want to research right now. We have good ideas later, like we can have stronger encoder, weaker decoder, or smaller or stronger decoder and smaller, weaker encoder. So now I'm asking Opus, let's say I want to do the following research with 4 different patch thresholds, each training this amount of steps, plotting graphs. What can I learn from this? What questions can I ask? What can I understand? So just this entropy threshold. So we can train 4 identical byte latent transformer models, thresholds 1.5, 2, 2.5, and 3. So this is rare splits, larger patches, for example. We can track training loss, validation loss, gradient norm, learning rate, steps per second, peak memory usage. Gradient norm, I don't 100% understand these metrics, but we will understand it. It's size of gradient norms, but I'm not sure what that means and for the model and for training. Maybe we don't want big gradient norms, it's unstable training, I'm not sure. Then we can do patch statistics like average patch size, standard deviation of patch sizes. I don't know if I like these statistics. I don't know what even we can learn from them, I'm not sure. So maybe we won't use these, or maybe we'll get them and give them to Opus and Opus will teach us something from them. And then separate losses for these: local encoder, latent transformer, and then local decoder. Research question 1. What is optimal granularity? The problem is I only have one GPU right now. I don't even have distributed training. So I can just train a little bit of my transformer. It will write cohesive language words, but it's not like scaling to the huge proportions. But we have to start somehow somewhere, so I'll just try this. I also need to learn how to scale these things onto multiple GPUs. Right now my code just works on a single GPU. So we're gonna look which of them converges fastest, which achieves lowest final loss, and is there a sweet spot threshold? I'm not sure what they mean by sweet spot. Maybe if one converges very fast and the other converges lower but needs a lot more compute to converge lower, maybe this one is the sweet spot, fast convergence. But I'm currently gonna train these things in like 5 minutes each. We would need to train them for more, 30 minutes, a few hours even later. And even then it's not too much of a scale, one GPU. We'll figure out scale later. It has hypothesis median thresholds, 2 to 2.5 will perform best, balancing semantic coherence with sufficient granularity. We have this question: how does patch size affect learning speed? Guys, honestly, I'm a bit tired, so I'm gonna link to the next video in the description to the second part. So I need to now publish this video and take a break. Check out my other videos right here, and see you next time.